next year. keeping a list. It's like pages right now. Okay. Okay. So we're doing 51. If you're just tuning in, because I forgot to record. So this is 51 from what? Chapter 6. Yeah. All right. So we changed our velocity to meters per second. We've got our airplane, which is poorly drawn here, and it tells you that the wings are inclined at an angle of 40 degrees, right? Okay. Now there are really only two forces acting on the plane. What are they? You guys tell me. Gravity is pulling it down. Is that going to in any way contribute to our circular motion? No. So does everybody see what the path is? The path is going to be a circle. It comes out of the board and goes around like this, right? Does everybody understand that?
So isn't that X force the centripetal force?
So exactly. So there's an X force that's going to provide our centripetal force. So like here's the center of the circle, right? So we have to have something pushing this way. So you guys said, well, there's lift. Well, yeah. Let's see, what does it tell us about that? It says, what's the radius of the circle in which the plane is flying? Assume the required force is provided entirely by an aerodynamic lift that is perpendicular to the wing surface. So here's our lift force, right? What should I do with that lift force? Split it up into components, right? So there's going to be a lift force in the y direction and a lift force in the x direction to replace that original force, right? Make sense? I guess I shouldn't have erased that vector. Let's leave it in there. It's a little sloppy because now I've got the same force we're counting twice. But all right. Do I know any of these forces? Start filling in. It doesn't even give us the mass of the plane, does it?
Nope.
Holy cats. All right. Well, so we don't know the mass. That's fine. Write everything in terms of m. So my force of gravity is going to be mg. Because the plane is flying in a horizontal circle, I know something about the vertical component of my lift. What does it have to be? It's got to be mg. Right? Just directed up instead of down, right? Okay. Thoughts? We haven't used the 40 degrees yet. So right now I've got it drawn as the angle between the wings and the horizontal. Does it show up anywhere else in my triangle? So it turns out if you go through a little bit of geometry that this angle here is also 40 degrees. Do you guys want me to walk through how I'm getting that?
I think that makes sense.
So it's because this lift vector here is at a 90-degree angle to the wings, right? So if this is 40 degrees, then that means that this little angle here has got to be 50 degrees, right? Follow? Right? Because they have to add up to 90 because it's a right triangle. Follow? So, and then these two red lines form 180 degrees. So if this is 50, then this guy over here has to be 40. Stupid geometry. Does it make sense? Did somebody say no? We good? Okay, cool. So now I've got this triangle. So here we go. Let's see. So we know that our lift force is that. We know that our lift force in the y direction is mg. We know that this angle here is 40 degrees. So what do I really want to solve this problem? Do I want my lift force or the x component of the lift? The x component, because that's what's responsible for our centripetal force, right? Does that make sense? Because it's what's pointing inwards towards the center of our circle, right? Okay, so let's see. Trig function, I'm going to use tangent. So the tangent of 40 degrees is the force of lift in the x direction over the force of lift in the y direction. Follow? If you missed it, I just wrote back. Okay, so that means that the force of lift in the x direction is mg tangent of 40 degrees. Well, that's my centripetal force, right? That's what's going to make the plane go in a circle. So if centripetal force is mv squared over r, then mv squared over r is mg tan 40. pause for a minute. Just did a whole bunch of algebra and geometry there. Did I lose anybody? Are you nodding because I lost you? Okay. Everybody happy? What's up?
Never mind.
You sure?
Yeah, I'm saying no to myself.
All right, so I'm looking at this equation down here. I notice that the m's cancel. Kabam. All right, I've lost track of what the question was. What are we trying to find here? Radius. Oh, right on. We're good. We know the velocity, we know g, we know tangent of 40, and we got to find r. So algebra and you're done. Make sense? All right. Questions with it? All right. So that was 51. 58 was on the list? Oh. There's got to be a better example of 58. Isn't that what we asked about, or was it 59? Oh, it was 59. Oh, good.
58C was the only one that confused me, though.
Okay.
I got everything else. Maybe by sheer luck.
I gotcha. All right. Well, let's put that on the back burner. If we have time, we'll talk about it. But that problem is, I really wish I hadn't assigned it. Okay, 59. That's one of the things on my list of things I'll do different. It's not assigned that problem. All right, 59. So it says in the figure, a 1.34 kilogram ball is connected by means of two massless strings, each of length 1.7 meters, to a vertical rotating rod. The strings are tied to the rod with a separation of 1.7 meters again, and they are taut, which just means the tension is not zero. The tension in the upper string is 35 newtons. What's the tension? Blah, 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 blah. Okay, so let's make a drawing. So here's L, here's L. They call this D, even though they're all the same thing. I don't know why they... So this is 1.7 meters. This is 1.7 meters. This is 1.7 meters.
Hey, that's an equilateral triangle.
Yeah. Let's see. We know that the mass of the ball is 1.34 kilograms. And we know that the tension here is 35 newtons. Okay. So that's it. All right. So thoughts about where to start, you guys? Sure. What do you got?
I tried to find the radius of the circle that it's.
Okay. That seems like a good idea. So did you just kind of do one of these
Yeah,
guys? Right. So that means that this is going to be 0.85 meters, and this is going to be 0.85 meters, right? Does that make sense? Like Alex pointed out, it's just an equilateral triangle, right? So these angles are 30 degrees. Stupid green pen. These guys are 60. These guys are 60. So you can find that missing guy either using trig or Pythagorean theorem. Good? All right. So if you figured out this radius, turns out to be, what's number 59?
Yeah.
1.47, is that right? Okay, so I'm good with that. We're probably going to need that at some point. All right, other thoughts? We're trying to find the tension in the bottom string. Isn't that the question A asks us?
Yeah.
Okay, so Caitlin, you got an idea?
Well, I did a free body diagram and then labeled the two tension forces.
Yeah, that's exactly what I would do. But all of the forces that we're interested act on this little ball, so let's make a free body diagram for the ball. What are the, let's name the three forces on the ball. What are they? Gravity, tension 1, tension 2, right? So let's call this one tension 1, and we're trying to find, the force of tension 2, right? Okay, so let's draw this thing. Here we go. Here's the ball. Gravity is pulling it down with a force of 1.34 times 9.8. That gives you 13.132 newtons. Good? All All right, my tension 1 has an x component and a y component. Force of tension 1 in the x direction, force of tension 1 in the y direction. And since I know the hypotenuse is 35 and I know my angle's 30 degrees, I can figure these both out, right? This one's going to be 17.5 newtons, and the x component turns out to be 30.3 newtons. Follow? All right, and then finally, this guy is going to have an x component and a y component, right? Force of tension 2 in the x direction, and force of tension 2 in the y direction, right? All right, so that seems good to me. Thoughts? Yeah, Alex, what do you got? Alex K. Yeah, these, the tension 1 in the y direction, gravity, and tension 2 in the y direction all have to add up to 0, right? Because the motion is horizontal. It's not accelerating up or down, right? Okay? So some of you guys are stumbling a little bit with sort of how to set this up. Please make sure you watch your signs, all right? I really wish I had made this negative because it's pointing down, and I know that the double negative stresses some of you out, but it's going to help you when you're solving problems, help you remember those negatives. All right, so what I want to be thinking about is this. I know that my net force in the y direction has got to be 0. So for me, that's the force of tension 1 in the y direction, plus the force of tension 2 in the y direction, plus the force of gravity. So 0 equals 17.5 plus force of tension 2 in the y direction minus 13.132, right?
Would it be minus FG21?
Right, yeah.
Let's go down to.
Oh, I gotcha. No, I'm going to put plus, and then the math will tell me that it's negative.
Okay.
Which is actually a really, really good problem-solving strategy, guys. Try as much as you can to let the math tell you the signs. Sometimes you get weird, surprising results where, like, you'll solve this and you'll get a positive, and you'll be like, wait a minute, my tension can't be up. I must have made a mistake. You know what I mean? So trust the equations to give you the signs. Don't sort of insert them yourself. Okay? I mean, unless, you know, like this one, we know that's negative, right? But because it's a known value, I guess, is the difference there. Okay, so go through and solve this mess. You find out that the force of tension 2 in the y direction, it does turn out to be negative if you do the math. And you get negative 4.368. Follow? Any questions? All right, right on. So that's the y component of my tension, and I know my angle, right? So here we go. Here's the force of tension 2 in the x direction, force of tension 2 in the y direction, force of tension 2. I know that this guy is negative 4.368. I know that this angle here is 30 degrees, so I can do a little trig and find this guy, right? Or I know it's a 30-69 triangle, so this guy's going to be twice as big as this guy, right? So use that if you want. You get 8.74 newtons. Make sense? Conceptually, why is tension 2 less than tension 1? What's tension 1 doing that tension 2 isn't doing? You got an idea, Alex? Sorry, I just didn't hear you. Yeah, exactly. Tension 1 is supporting the weight, right? And then some, right? The idea is if this string wasn't here, this is a really good way to think about it. If this string wasn't here, what would the ball be doing? Instead of swinging like this, it would be up higher, right? Right? But that other rope is holding it down, preventing it from going out more, right? Follow? All right. So that's part A. Are there questions on it? Okay. Part B. What's the magnitude of the net force on the ball? Okay, well, so can somebody give me an expression for the net force on the ball? Just what things are we adding together to get the net force?
Isn't it just FG1x plus FG2x?
Yeah, it's just the two x components, right? That was the whole point. Our y components cancel out. So my net force is just going to be the sum of the two x components, right? So to solve part B, I need to find F2x, right? So do a little trig, or a little Pythagorean theorem, however you want. And F2x turns out to be 7.57. And so now I can find my net force by just adding up my 2x components, right? So 30.3 plus 7.5 gives you the answer of 37 point whatever it is. Good? How are we doing? Okay. All right, and then question C. What's the direction of, what's the speed of the ball? Oh, gotcha. So this is, I think, where what I was saying at the beginning of the hour, now that comes back to help us, right? Let me do this. My board is getting a little cluttered. Aha, it worked. All right, so question C wants to know the velocity of the ball, right? Well, what equation should I be thinking about at this point? Trying to find the velocity or speed of the ball.
AC squared over R.
Okay, AC equals V squared over R. That works. I'm going to tweak it a scope because we don't know the acceleration yet, but we do know the force, right? And this boils down to the same thing because you're just dividing by mass. So there's nothing wrong with doing it this way. So remember, you guys, all of our acceleration is centripetal acceleration, right? Did I make a mistake? Sorry.
Oh, I just keep trying to do this when I get 6.4 meters. Saying 7.8.
Oh no. All right, well, let's see. One of us made a mistake. And if both of you guys got the same answer, then it might be me. So maybe that's the point. Let's see what happens. So let's see. Our centripetal force is the sum of those two x components. So that's 37.9 newtons. That's got to equal the mass of the ball, which is 1.34 kilograms, times v squared over the radius, which is 1.47 meters. Let's solve that. Yeah, that clearly doesn't, yeah. What are you getting?
6.45.
Yeah, I have your point. I see what I did. I squared my radius for some reason.
5.
Okay, so what are you getting?
6.45.
6.45 meters a second? Okay, my bad.
Oh,
I did add on 3 points, by the way, into that last test. I think I only owed you 2, but I gave you 3. Yeah. Oh, wait. 6.1, number 13. Oh, that's why. Okay. So 6.1, number 13. And what was this one? 59? Okay, got it. Okay, yeah, for some reason in my math I squared the radius. I don't know why. All right, and then finally the last one says what direction does something act? Net force. In my drawing it's left. Most importantly, it's inward towards the rod supporting everything, right? Good? I need to be better checking that. I did check that. I can mark it correct. So, okay. Are we good with 59? All right. So I think we've got time for one more. Was there one of these that dealt with friction other than stupid 58? I think it would make sense for us to do one where we're turning that deals with friction. Oh, really quick, just because I'm looking at it. Number 53, an old streetcar runs a flat corner of radius blah, 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 blah. With what angle will the hand straps go? That's the same as that question that was on the last test, right?
Yeah.
So make sure you know to do those. It's the second time we've seen one of those. 53. Is that on the list up there? Should I do that one real quick?
Yeah, go for it.
Oh,
I can do it.
do you want to?
No, I'm just saying I can.
Okay. So here we go. We know that we're going around a corner with a radius of 9.1 meters. We know that our velocity is 16 kilometers an hour. Skeptical, Alex. I'm sorry. That was correct.
Wait, what'd you say?
Nothing. I said 16 kilometers an hour, and then I said I'm skeptical.
Oh.
See, because just
Yeah, I didn't need to check. Wait, I did. I converted it this time.
Awesome.
That's why I got it right.
Okay, so there's our velocity. So what I'm going to do is I'm going to find the acceleration. It turns out to be 2.17 meters per second squared. All right. So the idea is, if this is your strap, so the car is, how do I want to draw this? Here's the streetcar. Front view, it's going around in a circle like this, coming out of the board and going around. Follow? Here's the hand strap, right? It's got to have, whatever, some amount of mass, right? So that tension vector is accomplishing two things. The x component, force of tension in the x direction, is mass times centripetal acceleration, right? Because the x component of the tension is providing the centripetal force. And the force of tension in the y direction is that. And we want to find this angle. Make sense? Or no? It's just the drawing. I know we're not done, but are we good up to there?
So what exactly is a hand strap?
So like on subways and streetcars and stuff, they have a little
Oh.
strap that
Oh,
hangs
that's
from
in a
the-
car?
Streetcar.
Oh,
so that you don't fall when you go around corners. Safety thing.
I'll just hold on to the handle.
Okay. Everybody good?
Good for you.
All right. So let's see. We're trying to find that angle. So I'm thinking about tangent because I know both of these guys, right? So the tangent of theta should be opposite over adjacent. Those cancel. So your angle is the inverse tangent of the centripetal acceleration over the gravity. Acceleration of gravity. So we know our acceleration, we know gravity. Acceleration of gravity. Good?
No.
What?
What? This hand strap screwed me up. You drew the picture of the box, and then the hand strap was going like.
So you're looking.
I don't-
You remember the airplane drawing where the airplane was coming out of the board?
Yeah. Oh wait, was that what was going on in the drawing too?
Yes.
Okay. Now it makes sense. That's why I was confused on what a hand strap was.
Gotcha.
You can still
Are we good? Everybody happy?
Yeah.
All right.
Wondering why the hand strap was like right.
All right. If there's time tomorrow, I'd like to talk about 54, but I don't think that's probably our best way to spend time right now.
Oh, yeah,
That's the one about the DFDR, DFPD, all that stuff. It's actually not as bad as it looks, but I know there's not going to be one like that on the test. So. What else is on the list right there? I have a list right here. 57 and 53, 47.
57.
57, is that you said? 57, there's not. Oh, did you guys last year do, this is like a very common physics lab where you've got, so there's a little plastic tube, which is probably a PVC pipe, and then you got a stopper, and you whirl the stopper around,
Yeah.
the stopper held up a little hanging weight. Did you guys do that lab
We
last
didn't do
year?
the hanging weight, but I remember.
Yeah.
Do we know what happened?
I gotcha. Okay.
Yeah.
Wait, no, we turned in one.
Okay.
One.
So,
Which one?
all right. So
It's a lab.
I'll set that up so you guys can see it. I'll set it up for you tomorrow, and you can at least see it as a demo. But so the idea is in this problem, you've got all right, so the idea is this little hockey puck thing is spinning around in a circle, right? Inertia wants it to go flying off in a straight line, right? But the idea is gravity is pulling this guy down, right? Now, the problem is set up where this little mass doesn't move, right? So what should your tension force be? Same as Ft, right? Ft equals Fg. Oh, well, that means that over here, my Ft equals my Fg, right? This Fg, right? So your centripetal force is just the weight of this little hangy dude.
And then you gotta convert it over.
So, Fg is capital Mg, right? And then the centripetal force on this guy is little m. So centripetal force is little m v squared over r, right? Did I lose anybody there? Okay, so then you just set the two things equal to each other. What are we trying to find? What speed keeps the cylinder at rest? Yeah, so we're going to solve for v. So if you set these two things equal to each other, you get v equals capital M G R over little m, and then you got to square root it, right? Just by setting this equal to this, and then solving for v. And then you just plug in the numbers.
No.
I'll do demo tomorrow. I'll set it up. It'll take like 2 seconds. All right. Other questions you guys want to go over here? Yeah, Alex, what do you got?
I was a little bit confused with 50.
With what?
50 is one with the graphs.
Oh, yeah. Nothing gross.
Why am I done? Oh, here we go. Oh, yeah. Gotcha. All right, let's see. An 85 kilogram passenger. Oh, so this is, what is this, number 50?
Yeah.
All right. So we got a passenger who has a mass of 85 kilograms. He's made to move along a uniform circular path with a radius of 3.5 meters. I'm being really sloppy about my significance. All right. Graph A is a plot of the required magnitude F of the net centripetal force for a range of possible values of the passenger's speed v. What is the plot slope at, this is a great one, actually. It says, what's the plot slope at v equals 8.3 meters per second? So here, it gives you this graph. So something like this. So v and f. All right. So what it's doing is it's saying, if you graph the centripetal force on the passenger as a function of his velocity, you get this graph. Well, you guys know this, because look, centripetal force is mv squared over r, right? Or in mathy speak, it would be m over r times v squared, right? So this is k times x squared, right? It's a parabola. Follow?
Yeah.
All right, and so the question wants to know, what's the slope when the velocity is 8.3? Well, how do you find the slope of a graph? You take the derivative. So I'm going to take the derivative of my force with respect to velocity. That's going to give me 2mv over r, right? And then you just plug in the velocity. And that gives you the slope at that point. Alex, does that make sense?
Yeah, I think I was just screwed something up. Yeah, I'll press some of these.
So, I mean, you know your mass and your radius, so you just got to plug in the velocity of 8.3. So that was part A. Are we good with it? I hope my answer is wrong again. It's right? Okay, good. All right, so everybody's good with A? Yeah. All right, so let's do B. All right, so part B says graph B is a plot of F for a range of possible values of T, the period of motion. Force against period. Right? So the idea is, as your period gets bigger, your velocity is getting smaller, so your force is getting smaller, right? But in order to make sense of this, we need to write an expression for force in terms of period. So, I know that force is mv squared over r. But I can't differentiate this with respect to period because period's not in it. So what am I going to do?
Substitute v for like that 2 pi over
2 pi r over t, right? So plug that in there. So my force is going to be m times 2 pi r squared over t squared, right? Times r, right?
Wow. I didn't know you could do that.
Could do what? Putting the t in the bottom like that?
Yeah.
I mean, we can slow it down. I don't mean that in a snarky way, like, I took a big algebra jump there. So it's m times 2 pi r over t squared all over r, right? So if you multiply the top and the bottom by 1 over r, that groups the r with the t.
Okay. I mean, I can see that, but I just don't know you can take the denominator out of a squared.
Yeah, because this just means 2 pi r times 2 pi r over t times t.
Yeah.
So you get f equals, what are we going to end up with here? 4 pi m r over t squared, I think is what you get. Oh, pi squared, sorry. Good? All right, so to take a derivative, you can use the quotient rule,
Or no.
or and then just take a derivative using the chain rule, right? So you get, take the negative 2 down, you get negative 8 pi squared m r times t to the negative third, and then plug in your period and you're done. Oh, sorry. Make sense or no?
That's
It's the
powerful.
power rule, exactly.
You said shade.
I did say chain rule, I lied.
Okay, I'm a little tired. So.
And, yeah.
With that? All right, are we good, you guys? All right, so tonight.